Hey guys! TypeScript is a programming language that was developed by Microsoft and released in 2012. It's a strongly typed programming language, meaning values in TypeScript are specified with a type. A type is essentially a set that defines the possible values that something can have. So this type only allows values with the string true. You can combine types together using the union operator, represented by the pipe symbol. So this type can contain either the value true or the value false.
You know that TypeScript already has booleans, right? You don't need to define them like that. And also, the already existing booleans are nicer because they aren't strings. They're literally true and false keywords.
Oh yeah, that's right. Also, this was just an example.
Also, you realize that TypeScript has
generic types. You were going to say generic types, right? Generic types are types that take in parameters. What are those parameters? Other types. So we can define a type like this. This type takes in a type t and contains a value of type t. So a box boolean can only have values of the type boolean. This isn't really useful at all, but it shows what a generic type looks like. Now let's make something a bit more useful. Let's define a new type called and give it two parameters, a and b. A and b will both extend boolean, meaning whatever we pass in must be something that can be assigned to a boolean. We can also use the extends keyword as a condition in a conditional type, which looks very similar to the ternary operator in JavaScript. So this line will return the value of b if a can be assigned to true, otherwise it returns false. Since the only thing that we can assign to true is true, this returns b if a is true, and false if a is false. And since b is itself a Boolean type, b should be either true, false, or Boolean itself. So, assuming we pass in actual Boolean values into and not Boolean itself, and will only return true if a and b are both true, and it will return false for any other combination, which is an AND statement. The OR statement looks like this. If you've messed around with lambda calculus before, these should definitely look familiar.
Well, that's nice, but is this able to do something other than booleans? Like, maybe doing math?
Sure, but to do math, we first need to define numbers. Num will be defined as a type with an optional property representing the previous number. The number 0 will be defined as a number whose previous number is undefined. In other words, 0 is specifically the number that doesn't come after anything else.
Wait, what? What about -1?
Negative numbers? Those don't exist here. And neither do floating point numbers. These are the natural numbers as defined by the piano axioms. And in that system, 0 is literally defined as the number that doesn't come after anything else. Because we need to start numbers somewhere. But anyway, now we can define a new type, next, which takes in type n extends num, and defines this new number as the number that comes after n. So we pass n in as the previous property. So we can define 1 as next 0, 2 as next 1, and so on and so forth. By induction, we can do this forever, so now we have all the natural numbers. Hooray! To convert these into actual readable literals, as opposed to just a long sequence of next onto 0, we run the number through this, which recursively converts the number into a tuple of underscores by peeling off next until it's undefined, and then we get the length of that tuple. So now, if we wrap a number with toLiteral and hover over it in VS Code, we can see the number written as a literal.
Hey, the reason why length works in the first place is because TypeScript also has...
Carl, now's not the time for that, because now we're going to define mathematical operations on those numbers. Addition is defined like this. We check if a is a 0 type. If it is, we return b. Otherwise, we return the value of add a minus 1, b plus 1. So each step, we decrement a by 1 and increment b by 1. Since we add 1 to b for each one that we remove from a, by the time we reach 0 in a, we have added 1 a many times to b. Addition. Subtraction is very similar. We just subtract 1 from both. For multiplication, we store a third value, accumulator. We add a to the accumulator b many times, and then return the accumulator. For division, we similarly keep a quotient value starting at 0. We subtract a from b until we hit 0, incrementing a quotient by 1 on each loop. And for modulo, we do the same thing as we do for division, but rather than keeping a quotient at all, we just return the value that a has on it on the last loop before the subtraction would go below 0. So now we have all 5 mathematical operations.
So this can do math, but is it Turing complete? Of course TypeScript is Turing complete, because in addition to all of this type stuff, TypeScript can also interpret a Turing complete language. I'm pretty sure that's where you were going. We can implement a version of Fractran in TypeScript. Fractran is a programming language invented by John Conway based on fractions. Fractran works as follows. Start with a natural number n as input, and a program that is a list of fractions. Starting with the first fraction, multiply the fraction by n. If that is not a natural number, go to the next fraction and try that one. Once you find one that does multiply to a natural number with n, set n to the product and go back to the first fraction. If we reach the end of the program with no natural numbers, the program terminates. For a more detailed explanation of Fractran and how to write some programs with it, check out this video by Derivative of X. So to implement Fractran, we first need fractions. A fraction is just a type that holds two numbers, a numerator and a denominator. When we multiply a fraction by n, we multiply a natural number by a fraction. So our multiply function can just return a fraction with the product of n and the numerator as the new numerator, and keeping the old denominator, because if we're multiplying a fraction by a natural number, the denominator is always just going to be multiplied by 1. But now we have a problem. If we multiply, say, 1/2 by 2, the result is now 2 over 2, which is a natural number, but how do we check that? Well, if we simplify this, it would simplify to 1, which is just 1 over 1. In fact, all natural numbers would have a denominator of 1 when written as fractions. So we need a function to simplify fractions in order to check if their denominator is 1. To reduce a fraction, as you probably remember from like 4th grade, you divide the numerator and the denominator by the greatest common divisor. So in 6 over 4, for example, the GCD is 2, so we divide 6 by 2 and 4 by 2, and we get 3/2. And we can compute the GCD with the Euclidean algorithm. Now that we have fractions, we can implement the Fractran step, which takes in n and a list of fractions. We take the first fraction f from the list and split it off from the rest. If the product of f and n has a denominator of 1, this step returns that product. Otherwise, it returns the Fractran step of n and the rest that we just split off, and checks the next fraction in the list. And of course, if our list of fractions is empty, we just return some sentinel value showing that the program ends, which in this case is just false. Then we just loop over the Fractran step until we reach the end of the program and return n. Of course, Fractran programs often run forever, so to ensure that they do finish, I added a system where you can cap the number of loops. That way we can always see a result. And now we can implement some of the programs from Derivative of X's video, like the doubling program. And since Fractran is implemented in TypeScript, TypeScript is Turing complete. Yeah. It's also Turing complete because it has all of JavaScript in addition to this type system. What do you think these types are for? What? Carl, why didn't you tell me this sooner? This would have been so much easier. Also, TypeScript actually has a hard-coded limit for how deep types can go, and the devs said specifically that they won't let you turn this off or let you increase it. But that doesn't matter, because I can change the source code myself and disable the check. This is probably fine, right? Special shout out to Tyler Zinke and all the other channel supporters. Thank you.